Happy to be opening this second day of the conference and to be able to talk to you all about underwater radiated noise from ships. In this talk, I want to give an overview of what's going on with regards to underwater radiated noise at the moment, and then focus on some work that we're doing at MARIN on this topic. So, as I'm sure you're aware, there's a big focus on air emissions from ships, including greenhouse gases. But of course, there are plenty of other pollutants, especially to the water, one of which is noise. And noise, underwater noise, is also recognized as one of the performance indicators, as you can see here. These indicators have been proposed by Green Marine, and they're used to certify ship owners and fleets in terms of their environmental credentials. So why is noise from shipping receiving attention at the moment? Well, it's been recognized that shipping is one of the largest contributors to anthropogenic underwater radiated noise. And here you can see a map showing the average sound levels from shipping in 2014, which clearly shows the higher noise levels where the main shipping routes are. Why is this important? Well, there's increasing evidence that noise from shipping has a negative impact on several different marine species. But one key difference compared to other pollutants is that a reduction of noise can lead to an immediate lowering of this impact. So we can, if we make a difference, then it's already immediately of benefit to these animals. One thing that's important to note, though, is that at the moment there's no international mandatory regulation related to underwater radiated noise of ships. However, there are numerous projects and initiatives ongoing at various levels, and I'll try to touch upon some of these during this talk. And of course, if we think about sustainability, then here are some of the main pillars or topics which we need to consider. And of course, noise relates to responsible use of the oceans. But what's also important is sustainable decision making, which I'll touch upon later, as well as financial solutions and innovation. And last but not least, communities and the roles of various stakeholders in effective mitigation of noise. So the rest of my talk looks a little bit like this. I'd like to give you an overview of the subject of underwater radiated noise from ships, and particularly focusing on a project we did last year called Sounds, in which we reviewed the state of play and consulted various stakeholders. And then I'll move on to a couple of recent projects at MARIN, just to give you a flavor of the kind of work that we're doing in this area. So the Sounds project. This study was initiated by the European Maritime Safety Agency in Portugal. We performed this work together with WAVEC, also in Portugal. And as I mentioned, the work focused on a literature review, as well as stakeholder engagement, which consisted of a questionnaire and some interviews. If you're interested in this project and the deliverable, then it's available to download from EMSA's website. So please go ahead and you can find a lot more detail in the report. So in this study, we focused on 4 main subject areas: noise sources, environmental impacts, policy, and mitigation, where the idea is that the first 3 come together to inform the 4th. So how do we select appropriate mitigation measures? And the main aim of the study was to deliver recommendations to the European Union about how to proceed with tackling the issue of underwater radiated noise from ships. So I'm just going to now go through these 4 main topics one at a time to give you an idea of what the most important considerations are and what's going on. So starting with noise sources. Here we can see an overview of continuous noise sources from ships. The main ones are propeller cavitation. At low frequencies, there are strong tonal components, but in general, broadband noise is important over, of course, a wider frequency range. And at very low frequencies, the machinery noise from the main engines can be the dominant noise source. And this is certainly the case below the cavitation inception speed. So with those noise sources in mind, we now look at how ship noise is measured, of which there are 2 main types of measurement, so-called dedicated measurements, such as sea trials. These may be performed by shipyards who have a noise requirement in their design, or classification societies. And there are also opportunistic measurements, such as for monitoring purposes, in order to track the changes in ambient noise in a particular area over time. And in order to perform measurements, procedures have been defined. Here we see an example from an ISO standard of recommendations of how to deploy hydrophones. And in general, these types of measurements are also important for the development and validation of noise models, which I'll get to in the next slides. Now, this field is developing quite rapidly, and at the moment there are alternative proposals to deploying hydrophones, such as the use of onboard sensors and even drones. So with onboard sensors, the idea is that you can monitor noise levels across continuously, so for a whole voyage, which provides more information and can be used for real-time decision making. And drones have been proposed as a cheaper solution for performing noise measurements. However, that's very much in its infancy at the moment, so we'll see what happens with that. Now a little bit about the standards. As I mentioned, there is an ISO standard for measuring noise, but it currently only applies to deep water conditions, while work is ongoing for a standard which can be used in shallow water, which is particularly important in Europe, but of course also in other parts of the world. Some other procedures have been proposed by classification societies and also by the ITTC, but we see some differences in the procedures in terms of how the measurements are performed and how the data is analyzed and corrected. And that leads to difficulties in interpretation of the results and comparison between ships and between measurement locations. And this has led to proposals for harmonization of the procedures in order to reduce this high uncertainty. And now moving on to modeling. Modeling in the context of noise mitigation is typically performed using simplified point source models. Here we see an example of a recently published model called the Echo Jomapans model. So here we have the frequency on the x-axis and the mean source level on the y-axis. and this model has been defined for 6 different ship types. So it's an empirical model, and it can be used in combination with, for example, AIS data to perform modeling studies into the effects of noise in a particular environment. An advantage of this kind of model is that the number of required inputs is quite low. So typically the speed of the vessel and something, a parameter related to the size, such as length or displacement. And these kind of models can be used to generate so-called sound maps, which are used for marine spatial planning purposes. There's an example here on the right for the North Sea. And you can see here the what's called noise excess. So the sound level in decibels of shipping above the other noise sources, such as due to wind. These kind of models can also be used as part of design, because they're computationally inexpensive, so they can be used to evaluate lots of different designs. But of course, they are simplified using few input parameters. So how are these sound maps generated? Well, you can use the AIS data, which is freely available, in order to look at the traffic density. Based on the traffic density, you can define the source levels and the noise footprint from the ships. Using propagation models, the sound level can be estimated at the receivers. So in this case, in order to generate a map, points are defined across the whole geographical area, and that allows the total sound field from all the sources present in that region to be estimated. And following that, statistics can be defined in order to be used for marine spatial planning purposes. Now moving on to impacts. So in this part of the study, we looked at a number of different species and also a number of different impacts. And just to give an overview here, we can see again on the right here the main noise sources from ships and over which frequency range they dominate, and then the frequency range is used by a couple of marine animals and the different kinds of sounds they make. Impacts can be wide-ranging from behavioral changes such as feeding and mating, through masking, where animals are inhibited from using sound to communicate due to the increase in ambient noise levels, up to physiological changes such as hearing loss. We can also look at this information in a slightly different way and compare the peak noise level from different types of vessels to the hearing ranges of different species, which is shown here. So we can see that, as you might expect, the larger vessels produce the peak noise levels at low frequencies, whereas smaller vessels do this at higher frequencies. So we have to be aware that the problem is very much specific to the location, depending on which species are present and which kind of vessels are present. Now moving on to policy. There are a number of different multi-party agreements in existence, although most of them are non-binding. There are also several different working groups concerned with underwater radiated noise from ships at different levels, both regional and international. And I'll go in a little bit more detail about what's going on at European Union and IMO level now. So at European level, we have the Marine Strategy Framework Directive, whose descriptor 11 states that introduction of energy, including underwater noise, is at levels that do not adversely affect the marine environment. And this is currently the only binding agreement concerning underwater noise in general. Of course, ships have to also comply with this requirement. And that means that the EU member states are obliged to address this issue. The frequencies of interest are specified, the 63 and 125 hertz. And the focus has mainly been on monitoring of ambient noise until now. This is achieved through a combination of measurements and modeling using the techniques I touched upon in the last few slides. And for example, this has been performed in the JONAPANS and JONAS EU projects. So here we can see how the descriptor 11 has been addressed over the last few years. And the focus was initially on monitoring and has now moved towards the setting of threshold values. So identifying sound levels which are above which a significant environmental impact occurs, which can then be used to inform mitigation. And the guidelines are currently under review. So there's this is an active piece of legislation which is leading to developments, research, and also updates of the guidelines. Of course, we also have the European Green Deal. Although noise is not explicitly mentioned in the Green Deal, it does fall under the categories of zero pollution and sustainable transport. And given the ongoing developments related to the MSFD, Europe is certainly actively engaged in trying to quantify and also reduce ambient noise levels from shipping. And if we move to the international level, then we are talking about IMO, and they actually published guidelines back in 2014, which concerned recommendations for reducing noise from commercial ships. This was, of course, only guidance and nothing binding. These are currently under review following an initiative from Canada. And a new version is currently under development and will be discussed in January of next year. In general, greenhouse gas emissions have received more attention so far, but now underwater radiated noise is certainly getting more attention, and yeah, the developments of standards and guidelines and regulation is accelerating. Another aspect related to policy is classification societies. Many classification societies have published noise limits and procedures for measuring noise over the last few years. Typically, vessels can comply with a transit, so a typical sailing condition or a quiet condition, which would normally a very low speed. Here's an example of different limits for a transit condition. And you can see that there are some differences between the different classification societies. It's important to note here that they're not always using the same terminology and quantities to measure the noise source levels, which leads again to difficulties in comparing noise levels from different vessels. So that's led to calls for alignment of the definitions, and also a proposal to distinguish between different ship types, sizes and design speeds, in order to have different grades or different levels of quiet ship, such that more vessels can comply with a limit which is reasonable for that category of vessel. So, of course, not that many ships have a quiet class notation. Historically, that's been research vessels, but also more recently cruise ships. The first was the Celebrity Eclipse, which you can see here. It's about 5 years ago. And actually last year, the first cargo vessel, a tanker, received a silent class notation. So it is possible for commercial vessels to achieve these limits, and we'll see what happens in the future in terms of improvement of the limits, but also ship designs in general, looking to reduce noise levels. And finally, regarding policy, I want to touch on voluntary certification, which, of course, again is not a mandatory legislation, but it's a way of ship owners or operators demonstrating their environmental credentials. And this doesn't just relate to noise, also to other environmental performance indicators. Such schemes can already be used, for example, to receive discounts on port dues, as has been implemented by the ECHO program at the Port of Vancouver. Green Marine is, as far as I'm aware, the only organization which includes an underwater radiated noise criterion in its certification program. Green Marine's been active in North America for about a decade, I believe, and also more recently in Europe. So I've already shown this slide, but just to go back to it, you can see here the different performance indicators which Green Marine use. And essentially, a ship owner can comply with various grades, various criteria in order to receive a certification for their whole fleet. And they are required every year to improve on one of these aspects. In that way, there's a momentum behind the process. There's initiative from industry to drive improvement in the absence of mandatory regulation. Now, a little bit more about the ECHO program. This initiative started in Canada due to the passing of some national legislation regarding protection of killer whales. And until now, it's the largest and most successful initiative focusing on noise reduction and mitigation of noise impacts from ships worldwide. So on the right there, you can see how the program is organized. So it's coordinated by the Port Authority with input from several different groups. So we have the acoustic technical committee, so the researchers and scientists. We also have the vessel operators involved, and also an advisory working group, which also includes other stakeholders, including indigenous population. So you can see that the important thing here is the involvement of a wide range of stakeholders in order to come to an effective solution. One example of the achievements of the ECHO program so far is the roughly 3 decibel reduction in ambient noise levels found during a voluntary slowdown trial, which they performed in 2020. So not all vessels complied with the slowdown, but despite that, a significant reduction in ambient sound was achieved. And then going back to incentives, the 3 levels listed here, gold, silver, and bronze, relate to different percentage of discount on harbour dues. And in order to achieve the various levels, you have to either have some technology which reduces cavitation on the propeller and therefore reduces noise, or a voluntary certification such as Green Marine, or a quiet class notation. And a lot of ship operators in entering the port have complied with these one of these levels. I believe that the bronze level is the most popular, and that may be related to the fact that these technologies such as pre-swell status or wake equalizing ducts also help to reduce greenhouse gas emissions and improve propulsive efficiency. And finally, moving on to mitigation. So effective mitigation is a complex task because the appropriate solutions depend on the species present in a specific area, the types of vessels present, and also economic factors. That means that decision-making tools are required, but these are currently not widely available. Here we can see an example of a tool which compares the habitat, so the areas in which killer whales are active, to the ship traffic density, in order to identify areas where impact may occur, and based on that to take mitigation measures. It's important to highlight that the trade-off with greenhouse gas emissions also needs to be considered. So, of course, in terms of regulations and also in terms of sustainability in general, we want to have a win-win situation here, but that's not guaranteed. I'll come back to that a little bit later, but we have to consider the whole. We can't just consider noise reduction in isolation and expect that everything else will stay the same or not get worse. And now I'd like to give some examples of mitigation measures, which are divided into technical measures and operational measures. So technical measures cover things like propeller design, so reducing cavitation, noise generating cavitation, changes in hull design, so improving the wake field, so improving the inflow into the propeller, which also reduces the cavitation dynamics, which is one of the main noise generation mechanisms. Isolation of machinery. So here you can see that the main path for machinery noise to radiate underwater is through the mountings onto the ship structure. So if you can isolate the machinery from the ship structure, then you can drastically reduce this transfer of noise through the hull plating. And another concept is air injection. You can generate essentially a bubble curtain around the aft part of the hull, which is designed to shield to isolate the noise radiated from the machinery, but also could also be from the propeller. In this way, you have a system which can also be retrofitted potentially. So there are various different options available, but it's important that they are considered early on in the design process in order to reduce the costs which come along with implementing one of them. Now we move to operational mitigation measures. So these are generally split into two categories. We have those which are for which the owner or the operator is responsible, such as real-time monitoring and maintenance. So real-time monitoring can be used to allow decision-making on the bridge in terms of noise levels. So the master can get a warning of when they're exceeding a certain limit, for example, and the system can advise what to do about that. Hull and propeller cleaning is of course important to reduce resistance, to reduce power requirement, but also therefore to reduce cavitation and noise radiation. Some operational mitigation measures are the responsibility of authorities. That includes marine spatial planning, the imposition of speed limits, incentives, as we discussed in the context of ports, and possibly also the use of noise labels. It's important to note that roughly 15% of vessels are responsible for half of the radiated sound power. So the focus should really be on the noisiest vessels in order to get the most benefit. On the right here, we can see a proposal of how to tackle the issue, starting with economic incentives focused on replacing the noisiest vessels in the short term, and then moving towards well-defined noise standards for new vessels. So taking noise into account throughout the design process, leading to new vessels being quieter overall. Of course, these standards don't yet exist, but by bringing together the various stakeholders, it's hoped that these kind of quiet vessels can become more common in the future. Now I'd like to show you a few results from the questionnaire that we distributed as part of the project. So we got about 100 responses from all over Europe, from different stakeholders, classification societies, naval architects, policy advisors, but also shipbuilders, ship owners. So a wide range of stakeholders. And we wanted to look at the relationships between the different stakeholders, gauge perceptions about mitigation measures, and also assess readiness for tackling the issue of underwater radiated noise and the possible introduction of mandatory regulation in the short to medium term. So we found that in terms of drivers and motivation for addressing the issue, environmental awareness was the most popular answer, with more than half of the participants saying that was their primary motivation. Policy was also mentioned a lot, despite the fact that most of the existing policy is guidance and not mandatory legislation. And economical benefit was a less common main driver, which may be related to the distribution of stakeholders who replied to the survey. In terms of preparedness, the majority of respondents said that we were unprepared or not well prepared for the introduction of regulations. And when asked what's the most critical issue for reducing underwater radiated noise from shipping, the most popular answer was improving the regulatory framework, followed by more research on environmental impact and mitigation. So we have an issue in terms of developing the legislation based on scientific work, but also we have the issue of engaging the industry in terms of being able to design quiet ships, so that when that legislation comes into force, we're prepared for designing and building low noise vessels. So this is just an overview of the key recommendations from the study. I'm not going to read them all to you, but the key words here are standardization of procedures. Measurements in shallow water are important. The development of management tools for marine spatial planning. Definition of thresholds for environmental impact. Updating the class notations. Increasing stakeholder engagement. And the use for the development of a quiet ship demonstrator. This is designed as a way of bringing together different stakeholders and engaging industry with the process of designing and building a quiet ship. It's also important to learn from the experiences of developing the greenhouse gas regulations, since this was, of course, a large effort which involved many stakeholders, and hopefully, in terms of underwater radiated noise, something similar can be achieved with clear procedures and limits. And it also want to point out that many of the above points are already being addressed in ongoing work. Hopefully in the near future there'll be some significant updates to what I'm able to show now. Now I've got about 5 minutes, I believe. So now I'd like to focus on what's going on at MARIN with regards to projects concerning noise from ships. So just to give you an overview, we have a number of different tools and facilities available for tackling noise. So we have simplified regression models for early design stage estimations. We have semi-empirical models for more detailed design predictions, which can also be combined with propeller optimization techniques to include noise in a propeller design. Then we also perform high fidelity CFD in order to try and predict noise and verify designs before they are measured in one of our facilities, the depressurized wave basin. In this facility, which we use for cavitation model testing, we have a dedicated silent towing carriage, which is used for noise measurements. So work on noise is performed through various different projects and initiatives. I'd just like to highlight a couple of those now. One of them is cooperative research ships. Here we work together with other researchers and industrial partners And in the context of noise, this led to the development of the so-called empirical tip vortex, or ETV model, which can be used to predict the noise from cavitating tip vortices of propellers. And this model has now been incorporated into our consultancy work. And now I'd like to show you some results from recent and ongoing EU projects. So one of them is called NAVIAS, and this was a Horizon 2020 project focusing on modular ship design, in which we looked at including noise in early design stages in order to reduce overall impact of ships. And an ongoing project is Saturn, which looks mainly at standardization, biological thresholds, and the assessment of mainly of technical mitigation measures where we are involved. So in NAVIAS, we looked at two main vessel types. One was a double-ended road ferry. The other was a workboat, such as an aquaculture vessel. The reason for this is that these vessels operate for a large proportion of time in off-design conditions. So in the case of the ferry, it spends a relatively large proportion of time decelerating, which leads to face-side cavitation on the propeller, which is known to cause high noise levels. And in the case of the workboat, which can spend a large proportion of time in DP mode, the propellers can experience large amounts of cavitation. So the goal of this project was to develop some new cavitation noise models for off-design conditions and implement them in an easy-to-use framework which could be applied during concept design of new vessels. So we did this by performing a lot of experiments in our depressurized wave basin. You can see a photo from a test of a cavitating propeller behind a thruster. We complemented those results with some CFD simulations, and that led to the generation of, or the development of new, what we call medium fidelity models, similar to the ETV model I presented on the previous slide. And by combining those results with standard series data for different propeller series, we could compute a large number of cases using a boundary element method, the results of which could be used to develop regression model, resulting in the simplified low fidelity model. So here you can see the results of the boundary element method analysis for the cavitating propeller. And here's an example result from the low fidelity model. This model has been implemented in a software tool called Auras, and the idea here is that you can look at the expected noise levels from the propeller, cavitating propeller, in different conditions. So not just steady sailing, as is required, for example, by classification societies, but also in when the vessel is accelerating or decelerating. And you can also compare the estimated noise levels to the limits proposed by the classification societies. And now I move on to Saturn. In this project, we are looking at two different air injection systems aimed at mitigating noise. One is a so-called prairie system, which is aimed at mitigating propeller cavitation noise by injecting bubbles into the propeller disc. And this kind of system is already applied to naval vessels, but has, as far as we know, not been applied to commercial ships. And here you can see a photo from one of our model tests. You can see the bubbles, air bubbles are injected through a duct upstream of the propeller. And we found up to 7 decibel of noise reduction for this system. And another system is the masker system, which generates a bubble curtain around the ship hull. This is mainly aimed at mitigating machinery noise. So we constructed a model scale metal ship section, which we excited using a shaker in the tank. And we injected air through porous hoses, which you can see here on the bottom right, in order to generate the bubble layer. And here's a photo of those from those model tests. You can see the bubbles flowing along the hull. And with this system, we measured up to 20 decibels of noise reduction. This is all ongoing work, and we're very excited to be able to report this next year. So yeah, hopefully I'll be able to update this in the near future. So some concluding remarks. I hope I've given you a good overview of the field of underwater radiated noise from ships, and demonstrated that it's very active at the moment, involving numerous stakeholders. The current focus is on thresholds, standardization, and trade-off analysis in order to define the best mitigation measures. And MARIN is engaged in a number of different activities, from concept design through to design verification and payload optimization, as well as background research on mitigation measures. So I'd just like to close with this slide, some food for thought, and something maybe to discuss. What are the win-win scenarios in terms of reducing both underwater radiated noise and greenhouse gas emissions from ships? So thank you for your attention, and if you have any questions, I'll be very happy to answer them.
Okay, we will start. Are there any questions from the audience? Yes.
George Smith, Lions and Angels. This might be a little bit outside of the discussion, but with the projects that you're doing, they had X amount of cases that you can drill down from to identify exactly what kind of design data you can actually choose from at that point. In similar cases that we have, we'll have some things where we'll have thousands of cases. However, when we're identifying through our requirements, we can drill down and make that case smaller. With that, though, on the other side of this is the costing. We also have a process of kind of identifying kind of a roundabout cost for each case. I didn't know if they had some similar type of tool that they can use to drill down even further, and which one is select in each case. So that's my question. I didn't know if you had something like that, part of the design part and the economical funding part.
Right. Thomas, I don't know, did you hear that question?
So is the question, do we consider the economic side of the cost benefit analysis of mitigation measures? Is that the question?
That's right. Yes, that's right.
We at MARIN, we don't do that directly. So we would have to work with partners to do that. But that is the aim in general, is of course to quantify that. So, for example, in the Saturn project, we're working on cost benefit analysis, and of course that requires input from industrial partners. So we are more focusing on the potential noise reductions of different technologies, which then of course need to be included in a cost benefit analysis.
Okay, thank you. Are there any other questions in the audience? Yes.
Yes, yeah, Laurent Corbel with Will Support NYC. Thomas, thank you very much for the work and also for updating us on that. I have maybe two questions on the ECO program in Vancouver. First of all, you mentioned some numbers on the discount on port use. So do I read that correctly, that it goes from like 23% to 47%? Did I read that correctly? It seems a big incentive. That's my point.
So yeah, that's the percentage discount you receive if you have a quiet class notation. Yeah.
Okay. And
so
yeah,
it's I guess it's a balance between how often do you call there and how much does it cost to achieve a quiet class notation.
and the second one is more because I know Seattle Tacoma is also working on a program asking basically to reduce speed in the budget sound. Does that happen elsewhere than on the northwest of the US? Those sort of initiatives?
Yeah, I think, well, it's important, to highlight that the ECHO program is not the only such initiative, and indeed on the west coast of the US there is another slowdown. Is it the I forgot the name. Is it this?
There's one in the Seattle Tacoma in the budget sound.
Yes, there's also one in California. I think it's Santa Barbara. But indeed, those appear to be the main initiatives, and I can't give you an answer as to why there aren't similar initiatives in other parts of the world. But we hope that in the near future that in Europe there will be a similar trial.
Thank you.
Yeah, thank you.
Hi, Vicki DeLugo, Kecky consultant. I was interested in when you were talking about the face side capitation. You wrote when you decelerate, but then I thought I also heard when you accelerate or decelerate for specific like ferries on a route going back and forth. Other than working on the face side capitation during the propeller design process, are there other mechanisms once the propeller is already designed that you can use, like maybe the prairie system or something like that, ducts, or to minimize face side capitation?
I think the prairie system could potentially, it can be applied on both sides of the blade. So yeah, I think that's possible. Of course, one option with such a ferry is to use a control pitch propeller and then to optimize the pitch setting depending on your mode of operation. So that requires you to implement a combinator curve, which is optimized for low noise. So that's one possible solution for dealing with face side cavitation if noise is a design requirement. Yeah.
Thank you.
There are a couple of questions online. Two of them are very similar, asking about the loss of efficiency or performance on propellers when the air bubbles are added. Can you comment on that?
Yes, so of course you don't want to lose, you don't want to reduce efficiency or lose thrust. So the main aim is with the prairie system is to dampen the collapse of the cavitation, which is what leads to noise generation. So in theory, you don't need a large amount of air to achieve that. So any associated performance loss would hopefully be small. And in terms of the masker system, well, it's designed to generate a curtain around the aft ship to shield the noise radiated from the machinery room. So the question is, does the air then flow towards the propeller? But I suppose in that case, the lessons learned from air lubrication systems would be transferable, and hopefully, again, in that case, the effect on propulsive performance would be small. But that is an important consideration when investigating these systems.
Well, thank you very much, Thomas.